Okay, previously we've kind of looked a little bit at sound waves and light waves, but let's look at them a little bit more detail on the human response to them. So frequency is measured in hertz, and it's really just how many waves would pass a point in a second, or how many full vibrations you would get a second. Now, in terms of sound waves, if we have a sound wave moving in this direction, a sound wave is longitudinal, so those vibrations are actually of the air particles vibrating parallel to the direction of travel of the wave. And humans can hear, if I draw a little here, those vibrations as long as the vibrations fall within a particular range. So um, humans can hear from 20 hertz all the way up to 20,000 hertz or 20 kilohertz. Okay. Um, so if an air particle vibrates 20 times a second, we can hear it. 30 times, we can hear it. All the way up to, and it's hard to picture it, an air particle vibrating 20,000 times in 1 second. Humans can hear those vibrations. However, that doesn't mean that air particles can't vibrate as part of a sound wave below or above that. So we do get air particles that maybe vibrate only 10 times a second. Everything about that sound wave is still there. We just can't detect it. We can't hear it with our ears. It's still a longitudinal wave. The air particles are still vibrating. Our ears and our brain just can't pick it up. Some animals can. So elephants can hear frequencies of sound that are below 20 hertz. And the same is true at the other end of the scale. So once air particles in sound waves vibrate faster than 20,000 hertz, we can't hear them. However, other animals like dogs, bats, dolphins can hear those sound waves. So this is really just human hearing, very specific to humans. It doesn't confine all sound waves. We call any sound wave that's below 20 hertz infrasound, and we call any sound waves above 20,000 hertz that humans can't hear ultrasound. Um, and you probably heard about all this in year 8. However, the same is true of light. Okay, so humans can see very particular, detect very particular frequencies of light. And they go from, I'm not going to change the color of my pen, but red, orange, yellow, green, blue, indigo, violet. And um, up this end is the increasing frequency. Okay, so we have this spectrum, okay, this range that we can detect. And as the frequency increases, how we perceive that is the color changes. So we start off at red and increase the frequency where we get more waves passing a point per second or more vibrations per second. It goes to orange, yellow, green, blue, indigo, violet. But we can keep increasing that frequency in the same way we can with sound. And in terms of physicists, what we'd say is the light is still there. We just can't detect it. Okay, so if we go above violet in terms of frequency, we get to something called UV. Okay, the light is still there. We can't detect it. However, other animals can. Once again, bees and some birds can detect in UV. So sometimes when we see like the petals on a white flower, it just looks plain and white, but actually in UV there'll be a pattern on it that attracts those animals. If we go even higher frequency than UV, we then get to X-rays. Still just like light, it will have all the properties of light. So if we think of the properties of light, they're all transverse waves. So UV and X-rays and visible light are all transverse. They can all travel through a vacuum. They all travel through a vacuum at the same speed. Everything about these other parts of this spectrum, exactly the same as visible light, only it's invisible. Okay. Um, if we go higher frequency than X-rays, we get to something we've encountered in year 11 before, which is gamma rays, okay? Which is just our normal gamma radiation. Gamma radiation, we say, was just a very high frequency electromagnetic wave. And this is our highest frequency, is our gamma rays. Likewise, we can do the same at the other end of the spectrum. So if we go at a lower frequency than red, our eyes don't have the ability to detect it, but it's still there, and we call this infrared. Okay. Still has all the properties of light. We've actually come across this before because this is heat radiation. Okay, so warm objects will emit this, where they aren't quite hot enough yet to glow red hot. They're emitting infrared. They're still emitting light. It's just light that we can't detect. We can't see. It's not visible to humans. Go below this, and we get to microwaves. And go below that, we get to radio waves. Okay, so you can see we have a wide range of light that is not visible. So this bit in the middle, this portion of it, we call visible light, and really just visible to humans. The other sections then have most of the same properties that that has, only our eyes can't detect them. Scientists, physicists would refer to all these as light, but we call this whole thing the electromagnetic spectrum. So visible light is just a small part of the electromagnetic spectrum, and it contains these 7 different regions. Okay, this is the highest frequency, so the frequency increases as we go this way. So this means that we have a very large or high frequency here, and radio waves are low frequency. As the frequency increases, the energy tends to increase, and we're going to look at dangers in another video, but that means that gamma rays tend to be a lot more dangerous than radio waves. But if you remember your equation V equals F lambda, the frequency is the number of waves we see per second. So it tends to be if we have a high frequency, the wavelength must be small. So down here, we have a small wavelength rather than radio waves. They have a large or high wavelength. Okay. Be careful in exams because these aren't always written with the high frequency on the right and the low frequency on the left. So they may be written in the opposite way round, so you have to kind of learn off the order, but we'll look at that in the next video.